to see the domain exactly because I was a little confused.
So x not equals 0. This is what we've been doing for 3 months, right? So the domain is x comma y with x not 0 and not 1. Anything else?
So that's what I did. So in that case, you just ignore the y, right?
Y can be anything. I'm not ignoring it. So the domain is consists of any ordered pair.
Beautiful, 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 beautiful.
Very nice voice, Rachel. Thank you so much. You entertained us today. X comma y can be anything, but x cannot be 0 or 1. Anything else? Other questions? Okay, so I would like us to talk a little bit about the interpretation of those derivatives. So when we talk about f prime of 1, let's say equals 3, this means a function that has, this is a derivative of the function, the value of the derivative of that function at 1 is 3, but definitely this means that the function has only one variable. So it means that at this point when x is 1, the function has a slope of 3. So the slope of this line is 3 when x equals 1, which also means the instantaneous rate of change. So at this point, the slope of this line, the tangent, gives the instantaneous rate of change. This is what we know from 2 months already. But what happens when I talk about df over dx, the partial derivative of f with respect to x at 1 is 3? What does this mean? Well, in this case, for a function of 2 variables, this is the z variable, not the y variable. This is the independent x, independent y, which means we're looking at something like this, where this is z, this is x, and this is y. Okay, so f of xy is a surface now. So it's not a curve on the coordinate system of x comma y, but it's a surface. Okay, so how does a surface look like? Imagine like a hat. So this is a surface. And this will be the f of x comma y. Now, df over dx means y is kept fixed. I don't know if I can nicely present this, but I have a picture from the book in a moment. So this means y is fixed. Let's say here is y fixed. When I draw this plane, the plane of y equals a number. It's fixed. That's why that means it's fixed. This plane will cross the surface. And when it crosses the surface on a curve. What does this mean? What this means, f of the partial f of respect to x at 1 is 3, is when x is 1, right here, somewhere here, the slope is 3. So a better graph, let me open, oh, I got a chat. Okay, we all agreed with that. We love that, good. So I would like to show better in the book, so I'm just clicking and clicking to get to the book. In the meantime, I can show it here. But it's better and easier if I show it in the book. electronically. I'm almost there. So see what happens? When we say that y is fixed, this plane cuts the surface over a curve. Imagine, maybe I can find my hat, any hat, and when we cut it, you will see a curve, right? And what does this represent? Well, this is the slope inside that plane on top of this function. And this is the rate of change at that point. Okay, I got to the text. So I just want the multimedia. I want chapter 6. I want find now. I really don't want all sections. I only want this for now. Okay. So we understand the difference between functions of one variable and functions of two variables in this case. And we want page 562, but I think it's going to open there eventually. Please. Where is my page 562? Why is it doing this? Oh, the next one. Okay, perfect. Fine. Okay, here it is. So here's the surface, which is f of xy. This is how it looks if you want to look from above on the plane x, y. We don't really need that, but I just want you to understand that what is good that they presented this is because this is the plane that is fixed for x equals fixed, or x equals a, or then y equals, it doesn't matter. So if we differentiate with respect to y, dz over dy, and we consider x fixed, x will be a plane, will cut the surface along this blue graph, blue curve, and the rate of change of this curve that is inside the plane will be our fy, in this case, the way they graphed it. So this is the curve C1, and this is the rate of change. So that's what dz over d, or df over dy, or fy. And that will be the slope at any particular point for any particular y value. So this is the y value here. If I want to draw the tangent here, then the y value will be here. But in general, is along this curve. It can be at this point, it can be at this point, it can be as they graphed it, it can be anywhere on the curve inside the plane. Okay, so now we know what that represents. And let's go back and choose a problem and work our way again through those partial derivatives, because we did not look at higher order partial derivatives. We only looked at one simple example, and then I ran out of time. Okay, so let's say problem 9 on page 567, and this is a function of two variables. It's e to 2x minus y. They're asking us to find fx and fy. Fx means I differentiate with respect to x. The other variable is fixed. Fy means I differentiate with y. The other variable is fixed. We consider it a constant. So fx, or df over dx, means this is e to a function. E to a function prime is e to that function times the function prime. I shouldn't write this because this symbol, and I will erase it, this symbol is specific for functions of one variable. Okay, so I'm going to erase this. So the question is here, I differentiate with respect to x considering y constant. So this is replaced by 2. When I differentiate this with respect to x, I get 2, and y is a constant. So I'm going to wipe out everything else. Don't write it like this, please. I just wanted to give you an idea to see what we're doing, but this is gone. So that's the answer. Yes, I will write it nicely as 2e to 2x minus y. Now fy is the same thing, but df over dy, which means we differentiate with respect to y. Everything else is fixed. Okay, same thing is e to 2x minus y. And when I differentiate this or this with respect to y, I only get -1 and nothing else. So negative e to 2x minus y. We do have, of course, second order partial derivatives and third order partial derivatives, but good enough. Second order partial derivatives. What are they? Okay, d2f over dx2. I differentiate f with respect to x twice, considering everything else constant. We don't like this notation per se. We like this notation. I differentiate with respect to x, everything constant, else constant, and I differentiate again with respect to x, everything else constant. Of course, we have d2f over dy2. We don't like this because it's cumbersome to write. We write this, fyy. And of course, we have d2f dx dy, which means I differentiate with respect to x and then with respect to y. We don't like this notation. We prefer this. And of course, I can have the other way around here. I can have d2f over dy and then dx. Of course, this would be fyx. Good. So let's see how we determine this. Let's choose a problem. Let's say 27. And that is on the same page, 567. And we have f of xy equals 7xy squared plus 5xy minus 2y. And they want us to find everything. They want us to find fxx, fyy, fxy, fyx. Spoiler alert, these have to be the same. Okay. Very good. So let's start. I cannot start with the second order derivatives, partial derivatives. I have to start with the first, of course. I can never jump to the second before I determine the first. Okay. So let's find fx. So this is our function. We are differentiating with respect to x. Everything else is fixed. So I differentiate with respect to x. Everything else is fixed. When I differentiate x, I get the constant. When I differentiate with respect to x, I get the constant. When I differentiate the constant, I get 0. Stop me if you have questions. Okay, f x x. I differentiate again with respect to x. There is no x. f x y. This differentiated with respect to y. Everything else fixed. Okay, I differentiated this with respect to y. I differentiated this with respect to y. fy. Everything else is fixed. I differentiate with respect to y. 7x, so 2, 14xy plus. I differentiate with respect to y plus 5x minus 2. fyy. I differentiate this with respect to y. I differentiate this with respect to y, 0. I differentiate this with respect to y, 0. Now I differentiate fyx. So this with respect to x, I get 14y. This with respect to x, I get 5. You'll see what we're going to do with all these in the next section when we determine max min for these functions. Let's look at a word problem. Okay, let's look at any questions on this. Do you need more practice with this? I mean, the next function will do that, but let me know. Would you like to work on another function? Would you like to choose? Let me share my screen. I can go to the next and the next, what page I want. I want page 567. If I find my, where's my keyboard? 567. Is this the keyboard? Yeah. Because I have 3 keyboards on my board, on my desk. Okay. So let me know if you want to choose something else. I chose, what did I choose? I chose this function. I chose this function. Let me know if you want to choose something else. Would you like to work on any of these problems? Is anyone with me?
Yeah.
Could you do 35?
Yes. Awesome. So let's take a look at 35. So in 35, we have f of x comma y, which is x natural log y. Perfect. Perfect pick. So they want us to find all 4 second order partial derivatives. Okay. So I have to find fx first. I differentiate with respect to x. Everything else is constant. Now fxx, no x. Now fxy, oh, 1 over y.